Hello everyone. Today let's look at a comprehensive practice problem related to functions. First, let's read the question. The question tells us that f(x) is an odd function and then asks us to determine which of the following conclusions is correct. Alright, let's look at the first one, which asks us to find the value of m. Now we know that if a function is odd, when a function is odd and we're asked to find the value of a parameter, what can we usually use? If the function is defined at x equals 0, then f of 0 must be 0. But kids, pay attention. This method only applies to what? It only works for multiple choice and fill-in-the-blank questions. For problem-solving questions, if we use f of 0 equals 0 to find the value of the parameter, we still need to substitute this parameter value back into the function and then prove f of negative x equals negative f of x, which is tricky. Many teachers forbid this method. If you can't use f of 0 equals 0, use the definition, apply f of x equals negative f of negative x. Otherwise, using f of 0 requires a proof even for multiple choice. We just need to use f of 0 equals 0, so let's see what f of 0 equals. It's equal to 1 minus 2 to the power of 0, which is 1, plus 1, which is 2. So 2 to the power of m equals 0, which is easy to solve. M is indeed equal to 2. So A is correct. No proof is needed for multiple choice or fill-in-the-blank ones. Now for the second question. Let's determine the range of this function on the interval from -1 to 2. First, let's write out the expression for the function. The analytic form is 1 minus 2 to the power of x plus 1 all over 2. We can use the properties of inequalities to work through this step by step. Since x is in the interval from -1 to 2, let's look at 2 to the power of x. You see, x to the power. Since x is between 1 and 2, 2 to the power of x is greater than or equal to 1 times 2, because 2 to the x is an increasing function. At x equals 1, the minimum value is 1 times 2, and it's less than 4 because 2 to the power of 2 is 4, but it's not equal. This is a strict inequality. Alright, so next we can find that this expression, 2 to the power of open parenthesis x plus 1 close parenthesis, is greater than or equal to 3 over 2 and less than 5. So what about its reciprocal? Therefore, we can get this 2 to the power of open parenthesis x plus 1 close parenthesis. The reciprocal is greater than 1/5 and less than or equal to 2/3. Then, what if we multiply by 2? Because the numerator here is 2, so multiplying both sides by 2 gives 2 here and 4 here, and then we add a negative sign, therefore we can get the negative of this expression. 2 to the power of open parenthesis x plus 4 close parenthesis over 1. This 2 here is greater than or equal to -4/3. Less than -2/5. Therefore, we can further find that 1 minus 2 to the power of x plus 1 in the denominator, this 2 is greater than or equal to, that is greater than or equal to -1/3. Less than 3/5. So let's see, we can't actually reach 3/5, so this should be an open interval, therefore option B is incorrect. Alright, next, let's look at option C. As for option C, kids, do you know what this is trying to tell us? What does it want us to determine? When it comes to monotonicity, remember there are two forms. One is this layered form, as long as the signs are consistent. Look, this is f of x1 and f of x2, and then this is x1 and x2. If it's greater than 0, it means the function is indeed corresponding within its domain. If it's less than 0, it's decreasing. The same logic applies. It could also be in this form, f of x1 minus f of x2 over x1 minus x2. If it's greater than 0, it means it's truly increasing within the domain. If it's less than 0, then it's decreasing within the domain. So why is this so remarkable? Let's talk about that briefly. Because let's suppose, for example, if x1 is less than x2, then this parenthesis is negative, so the product is greater than 0. Since this is negative and the product is greater than 0, it means that f of x1 minus f of x2 is also less than 0, so f of x1 is less than f of x2. And then x is still less than x2. So isn't this just true? So remember, you don't need to derive it again in the future. Just remember that the key is to keep the positions consistent. The positions of x1 and x2 should be the same in both places. If this part is greater than 0, it's increasing. If it's less than 0, it's decreasing. The form is the same. So let's see if this really holds within the domain of definition. Well, it's easy to check, because the expression for this function is 2 to the power of, here the exponent is 2. So if we think about 2 to the x, it's always positive, and adding 1 to it is still positive. So in the denominator, as the denominator increases, this fraction decreases, and then there's a negative sign, which makes it increasing again. So overall within this domain, it's indeed a true function. Therefore, option C is correct. Alright, you need to know how to use this method to make judgments. To repeat, it's about using this step-by-step approach. As the denominator increases, the fraction as a whole decreases, and then with a negative sign, it becomes increasing again. So overall, it's an increasing function. So this is correct. Next, let's look at option D. Once you understand option C, looking at option D becomes very simple. Just now, we already determined that this function is an increasing function. So this being less than that means 2x minus 1 is less than ax squared minus 2x. At this step, for Hengcheng's question, we just use parameter separation. By applying parameter separation, we can solve it. Let's take a look. If we simplify the expression a bit, we get x squared minus 4x plus 1 is greater than 0, which must always hold. At this point, we say this is a parameterized quadratic inequality that must always be true. For this kind of parameterized quadratic inequality, you need to see whether it holds for all real numbers or only on a certain interval. If it only holds on a certain interval, then that's when parameter separation is used. Or you can discuss it in segments. If it holds for all real numbers, then we use the discriminant method. It's clear that in this case it holds on R, so we use the discriminant. First, for the quadratic to be always greater than 0, we need to ensure that the parabola opens upwards and that the discriminant delta is less than 0. For delta, let's write it out briefly, a must be greater than 0, and delta, which is b squared 16 minus 4ac, so minus 4a, this value must be less than 0. Therefore, we find that a must be greater than. From the equation above, we solve for a greater than 0, and when both are greater, we take the larger value. In the end, we find that s is greater than 4. According to the rule of taking the larger value, we find that a is greater than 4. Now, this range we found is actually a necessary and sufficient condition for the proposition to hold. However, keep in mind that the question is specifically asking us for a sufficient but not necessary condition. Because we are looking for a sufficient condition, we simply need to identify a smaller range that fits within our result. The necessary condition must always be included, meaning the subset and the overall set share the same range. When you draw the graph for a sufficient but not necessary condition, the range should be smaller. Moving in this direction creates that smaller range. For instance, x greater than 5 is acceptable because it is a smaller range than x greater than 4. While x greater than 4 covers this entire area, x greater than 5 only covers this specific part. So that's why it is indeed a sufficient but not necessary condition. Now, what if we're asked to find a necessary but not sufficient condition? You just need to find a broader range. For example, what about x less than x? Greater than 1, as long as the range is broader than the original, that's fine. Remember, when solving problems about necessary or sufficient conditions, first find the range where it's both necessary and sufficient. Then, if you need a sufficient but not necessary condition, narrow the range. If you need a necessary but not sufficient condition, broaden the range. That is how we solve this type of problem. Therefore, the final answers are options A, C, and D.